Worksheet to see the design of a trust member. So also the concept of design. The 4-bay trust below. So 4-bay is base, as you can see, 6 feet by 4 is 24 feet span. Made by the aluminum 2014 T6, and they give us the normal yield stress. So this is the sigma failure. The truss member have a circular cross section, so it will be the circle. Circular bars are available all sizes up to 3 inches with the 1/4 inches increment. So based on my explanation in worksheet 2B, you know what is that about. So in this case, up to 3 inches. So in the market, they go from, for example, in this problem, it will be 1/4 inches side. Then you have 1/2, you have 3/4, you have 1, you have 1 and 1/4, etc. until 3 inches. So that where the size you need to choose from. Then using the factor of safety of 2 with respect to the yield stress. So that here it yields, so basically the normal, design the member CD, where the member CD. And of course, you design other member exactly the same. Member CD, that is the member of interest. Member of interest CD. And as you can see, that member of interest, you need to do the cross section. Go back to worksheet 1B, 1C. We do the truss in lesson 1. Or go back to your engineering mechanics. We do the section cut in this case. The section cut there through the member of interest. And as you can see, it's better to choose the one on the right segment. So from that, we need to find out what is the EY, what is EY, the support reaction Y, and of course you can also have this is a pin, so you have EX, but for sure only the vertical load, so you have it EX equals 0. Otherwise you can sum up all the force in X direction, the EX equal to 0. And of course this is roller, you have AY. So with that we design for member CDs. Let's continue. Design CD, that member. And first we find out external forces. And use the free body diagram for the whole truss and take moment about A so that we can find out EY. EX already 0 as I mentioned. So that one is use your very good engineering mechanics. I assume clockwise is positive equals 0 about A, so you have it 10 times 6, then plus 6 times 12, and EY negative because clockwise times 24. And from that we can have EY equal to 5.50 kips in this case, so kips going up positive. So from that we need to find out to determine stress, we need to find out the internal forces. That is the second step. For those of you forget about that, go back to the lesson 1. So it will be internal forces. So do the section cut, and consider the right segment. So we will have member EF, member ED, member EF, FD, and then we have CD here, FC, and then we have FG. So from that we can have the load here is FG, load there is FC, and this is member CD. That's really the member we care about. So instead of the node, we have the join F, join D, and join E. And join E, we also have the reaction EY equal to 5.5 kips. 5.5 kip. And that's it we have. And go back to put geometry. That one, its span, each bay equal to 6 feet. And the height, 8 feet. So from that, to find out CD, we don't need to find FG or FC. Even we can do that. But let's take moment about F to find out CD, because the FG and FC go through F. So let's take moment about F and assume clockwise positive. So you will have CD times 8. And then you have EY 5.5 kips about F is clockwise, so counterclockwise, so negative 5.5, and the base is 6 feet, so you have 6. From that we get CD, that internal force of member CD 4.125 kips, and if positive, it means the member in tension T, which makes sense, as you can see with the load here. The bottom member AB, BC, CD, and DE is all in tension. The top members AH, HG, GF, FE should be in compression. So from that, we can go ahead to find out stress. So you can see external force, internal force, and stress. So the next step, it will be stress. Okay. So stress, we have what? The actual less than allowable. And the actual in this case is about sigma. So sigma actual less than or equal to sigma allowable. I make a short now. And that is equal to P, the load, over AT less than for the normal stress, sigma allowable. So it equal to sigma fail, that given, divided by the factor of safety. This sigma fail is 58 KSI. Do you know where that come from? Go back to appendix. Which appendix? Appendix B. And in this case, again, it's US customary unit. You go to aluminum 2014 TS. And in this case, normal stress, you see yield strength for that is 58 in here for aluminum alloy 2014 TX, 58 KSI. See that one? So that even they don't give us the number, we can go back to the table to find that out. So from that, we can quickly, similar to the first two problems for today's class, we can find out D greater than or equal to 4, because that is areas is pi, you recall pi d squared over 4, right? So it's 4 times the load 4.125 times the factor of safety 2, divided by the pi, let's write pi here so we can know, and time the sigma fail, so it will be 58, and that's square root. Where that come from? Go back to problem here, you have that, right? You have to go back to the problem 2b, and then even go to 2a, you also have that same equation. That's why I go fast in here to find that down in that one. So with that, we will have d less than or greater than 0.426 inches. And the problem give a choose the diameter in the 1/4 inch increment. So I showed you earlier, it can be 1/4, 1/2, 3/4, 1, 1/4, etc. until 3. And the nearest, you have to jump up to the 1 because it have to be greater than or equal to yes. So as you can see, it should be the chosen one. It should be the d equal to 0.5, right? So from that, you choose d equal to 0.5 inches, and that should be the answer, because that should be the nearest from here to there. It will be the nearest 1/4 of inch. Make sense? Before we choose that. And now the question asks number 2, what is the actual factor of safety after design with the respect to proportional limit stress? What is that about, proportional limit stress? We will talk about that next class, lesson 3. But now it's actually the same as the one we just do in worksheet 2b. So just get that done in here. So actual factor of safety, that would be fast. Actual factor of safety. So the factor of safety is always equal to the sigma fail divided by, in the equation, sigma fail over sigma allowable. But I already explained, if you find out the actual factor of safety, like in problem 2b, the allowable now, because it's become an actual, so it's actual here, tau fail over excuse me, tau actual. So we do the same in here. Instead of tau, now we put it sigma actual, because this is actual factor of safety. The regular factor of safety is sigma fail over allowable. Now it's actual. You know, that actual factor of safety. So from that we can plug in fail is 58 KSI divided by sigma actual. So the force given for the force that we find out for member CD, 4.125 gives tension. So 4.125 divided by the areas, the actual areas based on the diameter we choose. So 5.5 square, 0.5 square, and we divide by 4. And from that, we can get the factor of safety equal to 2.76, which makes sense because the original factor of safety is 2. And when you design, you jump up the diameter. 0.426 is enough, but we jump it a little bit bigger size, 0.5 inches. The factor of safety is a little bit greater. In this case, 2.76. That concludes our problem 2C.